Okay, Unit 11, Vectors, Day 7. We're going to use all our knowledge of vectors so far, including how to do operations to obtain some vector resultants, but with some applications to them. Let's take a little warm-up. It says we have a component form vector we need to create out of a magnitude of 6 and a direction of 140. If I was going to sketch that, just to have a little context, 6 long, 140, I'd be a second quadrant vector. Therefore, I'd expect a negative x and a positive y for my components. What did we use to find component form? We said magnitude cosine of angle, comma, magnitude sine of angle. 6 cosine of 140 gets negative 4.6. 6 sine of 140 gives 3.9. Perfect. All right, let's start doing stuff. Looks a lot like physics to me. Force vectors acting on an object. Forces magnitude 20 pounds and 35 pounds. They act on the object at an angle of 48 degrees. Find the magnitude of the resultant to the nearest tenth, the direction of the resultant as a degree from the larger force to the nearest tenth. Use two component form vectors and vectors addition to find this resultant. Love it. All right, first of all, when doing an application problem, always place one vector on x-axis. In other words, it's always going to be an x coordinate only, y will be 0. So I'm going to take the larger of the two. I'll explain to you why in a minute. I'm going to draw it horizontally completely from the origin. If it's 35 and it's all horizontal, that vector is 35, 0. From that vector at a 48 degree angle, notice they're not both 48 degrees. One is 48 from the other. The magnitude is 20. I'll try to be somewhat to scale. And the angle between the two is 48. Now, if we wanted to find that resultant, we could copy vector red, copy vector blue, and the resultant is that diagonal, correct? That parallelogram method. It's also the sum of the two vectors if I had them in component form. Blue I do, red I don't. But as we just did in our warm-up, we can get that no problem. Magnitude cosine, magnitude sine, 20 cosine 48, 13.4, 20 sine of 48, 14.9. If I take vector blue, which is all horizontal, 35, 0, and add it to vector red, resultant vector r, which is equal to vector u plus vector v. My resultant is 48.4, comma, 14.9. Haven't answered the questions yet, but now they're easy. I have the resultant vector in component form. How do I find its magnitude? I'm going to use some symbols. Double bar absolute value is magnitude of r, the square root of x squared plus y squared. 48.4 squared, 14.9 squared, added up and square rooted. That magnitude is 50.6. Direction of the vector, again, symboled as theta, r equals tan inverse of y over x to the nearest, what do we say, tenth of a degree? 17.1 degrees. So again, the plan of attack, we took the two force vectors, put one on the x-axis, aka all horizontal. We got the other vector by using our magnitude direction, magnitude cosine, magnitude sine. Green came from being the sum of the two vectors, and then we could find a magnitude and direction. Let's attack another one just like this. All right, before we do this airplane problem, we're going to share a little bit of navigational conversion. If we have mathematical angles, what do they mean navigation-wise, and vice versa? And remember, if we did our math angles, we'd say 0, 90, 180, 270. So 35 would be in the first quadrant. First quadrant, we said, was northeast versus the other two axes being south and west. So we're always going to find the angle by taking its complement, because we always want to be off the vertical axis. So if that right there is 35, what I really want is off of north. So we're going to go 90 minus 35, which is 55. And now we're going to attach the two compass headings for the quadrant. So in this case would be north 55 degrees east. That's the way the problem will be given. This is the way we're going to do our calculations. Let's do two more. 150, second quadrant angle. This time we're going to do 150 minus 90 because it's beyond 90 degrees. 150 minus 90 is 60. But if I'm in the second quadrant, I am now northwest. I'm 60 degrees to the west of due north. And the last one, 195. I'm beyond 180, so now I'm going to subtract it from 270, the other vertical axis. 270 minus 195 is 75. I'm in quadrant 3. Quadrant 3, we said, was southwest, so I'm south 75 degrees to the west. All right, just for practice, let's go the other direction. If we have a south 25 east, what are we going to call that math-wise? South 25 east, I'm in quadrant 4. I'm 25 to the east of due south. So due south is 270. I'm going to add 25 to it. In my math language, I'm going to use a 295 degree angle to represent southeast 25. And then we have northwest 62. Again, let's get a reference where we are. Northwest is quadrant 2. That 62 is right there. I'm going to do 90. 62 off of 90. So I'll do 90 plus that 62, which equals 152 degrees. Again, the angles we're going to use in our computations will be the math angles, the green angles here. We'll be given them, however, in navigation. So let's attack one. We're still going to use our vector additions and resultants. All right, let's read this problem. An airplane's traveling at 300 miles per hour at a heading of north 40 degrees west. The wind's blowing in a southwesterly direction at a speed of 80 miles per hour. What's the ground speed of the airplane? Since we're looking for speed in question A, that means our velocities are going to be our magnitudes. So I'm first going to draw my blue vector with a magnitude of 300 and a heading of north 40 west. I'm going to convert that north 40 west from navigation to an angle we can use between 0 and 360. It's 40 beyond north, 90 plus 40. A north 40 west is a 130 degree angle. So I'm now going to draw that blue vector starting down here, nice and long, 300 in magnitude, and that angle I'll draw it the first time is 40 to the west of due north. The wind is blowing in a southwesterly direction, but no number. Magnitude's 80, I got that. But what's the direction going to be? If there are no numbers, that means 45 degrees in the middle. So where that would go is southwest 45. I'm going to try to draw it to scale. That's about 80. So that would be 45. And again, let's convert. Southwest would be 270 minus 45, which is 225. So to find the component form of vector blue, magnitude cosine angle, magnitude sine angle, 300. Cosine, 130. 300. Sine, 130. It's a second quadrant vector. I'm expecting a negative x, which I get, negative 192.8, and a positive y, which I also get, 229.8. Vector red, third quadrant. Both coordinates should be negative. How am I going to find this? Again, we use that 80 for the magnitude, cosine of 225, 80 sine of 225. Component form vector red, vector wind, negative 56.6, comma, negative 56.6. Why did we expect that? Because it's 45 degrees equal south and west. All right, we've set it all up. We're ready to find our resultant now. How do we find resultants? I like the parallelogram method. I'm going to repeat my vector red and vector blue. I'm going to draw in my resultant, vector green. I'm going to find R by adding U plus V, U plus V. Negative 192.8 minus 56.6, comma, 229, whoops, let's go in blue, 229.8 minus 56.6. Vector green, the resultant vector in component form is negative 249.4, comma, 173.2. A second quadrant vector, but if we looked at our sketch, somewhat to scale, that is definitely a second quadrant vector. All right, haven't answered either one. Haven't found the ground speed of the airplane or the actual navigation heading with the wind moving it off its course. But it's easy now. We've done all our work. I'm going to go back up, put a little note here. Ground speed, what's that mean? Magnitude of the resultant vector. Okay? Once we find the direction, we'll do that same navigation that we've done before. So how do we find the resultant's magnitude? Tool we've had for a couple days now. Negative 249.4 squared plus 173.2 squared. Add them up in square root. The actual ground speed of the plane is 303.6 miles per hour. So what did the wind do? It sped the plane up about 3.5 miles per hour. Knocked it off course too. Let's figure that out. Theta of R always equals tan inverse of y over x, 173.2 over negative 249.4. Theta. Whoops. Sorry about that. What are we doing? Need a little more room here. There we go. Let's do this. I got theta to equal negative 334.8, pardon me. Okay? Now, that negative angle is in the second quadrant. So that really means what we're going to do is we're going to add that to 90 and add some headings.